is about the past paper. For phase 2, it requires calculation of transverse BM and longitudinal BM. So the question is, the half ordinates of vessels water plane areas spaced 20 meters apart are 1, 13, 24.5, 33, 35, 35.3, 34.8, 31, 25 and 5 respectively, commencing from forward end. So the first ordinate 1.0 is at the forwardmost ordinate, and the last ordinate 5.0 is at the aftermost end of the ship. So forward to aft. Saltwater displacement of the vessel up to that water plane is 115,000 tons. Calculate her transverse BM and longitudinal BM. So what is transverse BM and what is longitudinal BM? See here, this is a ship cross-section view of a vessel, and we can see that center of gravity, center of buoyancy and initial center are all in one vertical line. So this is BM here, is marked. It is the initial metacenter. How did this metacenter come? You see the same ship is now heeled to starboard side due to external forces. So the center of buoyancy shifted from B to B1. Now the vertical which we draw up from B1 meets the center line of the vessel at N. This is transverse metacenter, initial transverse metacenter. Why transverse? Because this is transverse movement of the vessel is taking place. Port starboard or the rolling motion is the transverse movement. So when the transverse movement has taken place and the center of buoyancy has also shifted transversely from B to B1, that's why it's called transverse metacenter. And its initial metacenter, because up to small angles of heel less than 15 degrees, it is considered fixed, means not changing much. So almost fixed value. So for stability purpose calculation, we consider it fixed up to small angles of heel less than 15 degrees. That's why it's called initial metacenter, transverse metacenter, and GM in this value is also called initial GM, because as the ship heels more at large angles, this metacenter will also shift and GM will also change. So it's only the initial GM which is considered as fixed up to small angles of heel. So what is here to be noted is that this BM is also called metacentric radius. Why? Because if we plot various positions of center of buoyancy as the ship heels some more from B1 to B2 or B3 port and starboard, we see that the center of buoyancy is following an arc of a circle whose center is metacenter M and radius is BM. So BM is also called metacentric radius. We also need BM for calculating the GM because we need KM. For KM we need to know KB plus BM. That gives us KM, and then KM minus KG will give GM. So that is why it's important to find the BM. This is transverse BM because it's related to transverse motion of the vessel. Now when the ship is pitching or trimming, trim by head, trim by stern, or the ship is pitching at sea, again the same thing happens. The center of buoyancy will move. Now in this diagram, the ship has trim by head. Forward draft is more than the aft draft at new waterline W1 L1. So the forward volume, underwater volume is more than the aft. So B shifts to B1. Now when we draw the vertical upward from B1 Again, it meets the center line, but now we call it ML, longitudinal metacenter, because the ship's movement is longitudinal. Pitching motion is longitudinal movement, and the center of buoyancy is shifting also longitudinal from B to B1. So this is the transverse. Why? What is transverse BM? What is longitudinal BM? Longitudinal is related to the longitudinal movement of the vessel, and transverse BM is related to the transverse movement of the vessel. Now, the second important thing is the axis of rotation. So, when the ship is rolling, that is transverse movement. So, in that moment, what is the axis of rotation? What is the axis about which the ship is rotating? That is the axis is the center line of the vessel along the length of the ship, longitudinally axis along the length of the ship, center line, also called center line of the ship, which is passing through center of rotation. So for transverse, there is transverse movement, the axis is longitudinal. And similarly, when the pitching is taking place, it is taking place about transverse axis. That axis is transverse, it is along the breadth of the vessel. So here the two axes are marked. CL is the center line passing through F. F is the center of rotation, which is on the center line. So when we calculate BM transverse, we need moment of inertia transverse upon underwater volume. So transverse moment of inertia, we take the moments about which axis? About the center line, which is also called x-axis, passing through center of rotation along the length of the vessel. So moment of inertia we find is a transverse moment of inertia, and the axis is the center line of the vessel. CL, here you can see CL is marked as center line axis. But my half breadths, which are my ordinates, half ordinates, they are perpendicular to the axis. So when the ordinates are perpendicular to the axis, how do we proceed with the calculation? Because we have to take moments. Moment of inertia needs an axis, and the moments are taken as it's a perpendicular distance. The distance is the lever is perpendicular distance. So in this case, the half of the length of the ordinates is the lever. But when we do the Simpson, so as per the integration method, it is y cube function. Y cube is the y is ordinate, y cube dot dx upon 3. That is the function. So 1 by 3 is taken out, and we calculate y cube dot dx by Simpson's rule. For calculating BM transverse, first write the half ordinates forward to aft as given in the question, first column. Then find the y cube. Write the cubes of all the ordinates, like cube of 1, 13, cube of 13, cube of 24.5, cube of 33, cube of 35, like this. Cube of all ordinates is called y cube. Now we have written cube of all ordinates, and then I write the Simpson's multiplier. Which rule to use? If you count 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 ordinates are there. Rule number 1 cannot be used. So I must use rule number 2. So for Simpson's multiplier, for rule 2 or 1, 3, 3, 2, 3, 3, 2, 3, 3, 1. So y cube is multiplied with the Simpson's multiplier, and I get the straight away moment of inertia function. Products for moment I is the for moment of inertia, symbol for moment of inertia, we use I. And I see CL, small subscript CL means about central. So this is transverse moment of inertia, and it is about the central line of the vessel passing through center of rotation. We add up the I moment of inertia function, sum of the product 603831.69 summation 1. So remember, as I said, that we are calculating y cube dot dx upon 3. This is the integration. So that upon 3 is still there. So the sum of the product must be divided by 3 when we have coordinates which are perpendicular to the axis. So what is the moment of inertia about central line? This is transverse moment of inertia. Simpson's coefficient is 3h by 8. H is given in the question 20 meters. Then summation 1 from here and divide by 3. So summation 1 must be divided by 3 when we have the ordinates which are perpendicular, vertical to the axis about which moments are being taken. And we are doing with the y cube function. So sum of the product is divided by 3. And now that we have half ordinates, so in order to get the moment of inertia of the full water plane area, I must multiply by 2. So 3h by 8 into sum of the products upon 3 into 2. So 3 into 20 upon 8. Then I take the summation from here, 603831.69 divided by 3 and multiply by 2. I have one video in the past where you can see how it is derived. Then y cube dot dx upon 3. So here I get now BM transverse, which will be moment of inertia about the center line, transverse moment of inertia about the center line upon underwater volume. So I got the moment of inertia 3019158.45. Underwater volume is displacement upon the density 115,000 upon 1.025. So this is the 112,195.122 is the underwater volume which I insert here, I upon V, and I get 26.91 meter is transverse BM. So here in this case, I get straight away the moment of inertia. Why? Because remember, moment of inertia is about the axis which must pass through center of flotation. My axis must pass through center of rotation, and you can see that my axis here is the center line. Center line of the water plane is my axis, and it is passing through center of rotation because center of rotation must be on the center line. So I don't have to do any parallel axis theorem for this moment of inertia because the axis is already passing through center of rotation. But now when I go to do the BM longitudinal, BM longitudinal means the longitudinal movement of the vessel is taking place, like pitching motion. So that movement is taking place about transverse axis, which is here YY. Along the breadth of the vessel, the axis is running along the breadth of the vessel, transverse. Again, must pass through center of rotation. Axis must pass through center of rotation. This is called centroidal axis. So, I don't know the location of center of rotation. So, what I will do, I will find moment of inertia about aft end. You have a full choice. You can find the moment of inertia about any end, forward end, or aft end, or you can even do midship. It's up to you. So, just for example, I have taken my moments from the aft end. AB is the axis which is parallel to the centroidal axis, and it is coinciding with the aftermost ordinate given in the question. That 5.0 is the aftermost last ordinate in the aft side. So the axis AB, I take moments about this axis. So I will get moment of inertia about AB. Then I will apply parallel axis theorem, and I will get moment of inertia about the center of rotation, y. So these are the two axes. But I need to know this distance of the center of rotation, because for parallel axis theorem we need distance between the two axes. So this one here, our ordinates are parallel to the axis. See, axis is AB is axis, and YY is the centroidal axis, and parallel to it is the axis AB at aft end. My half ordinates are also parallel. So my ordinates, when ordinates are parallel to the axis, we don't do the cube function. We will just do our normal. We'll take the levers from aft end, and they will be multiplied twice. So area function multiplied by the lever, get the moment function again multiplied by the same lever, and you get the second moment of area function or moment of area function. The levers will be in terms of h now. Here we will find longitudinal moment of inertia IL, and the axis will be transverse axis. Transverse axis passing through center of rotation. Axis will be transverse. Transverse means along the breadth of the vessel. That will be the axis. So again we write the half ordinates, Simpson's multiplier, then area function, ordinates into Simpson's multiplier gets the area function. Now I take my levers. I have taken levers from aft end. You can take from forward end or midship, wherever. So which is my aft ordinate at the aft end? Ordinates are written from forward to aft. So this 5.0 is my ordinate at the aft end. So I take levers from here. So this lever will become 0h. And then moving forward, 1h, 2h, 3h, 4h, 5h, 6h, 7h, 8h, and the forwardmost ordinate will be 9h. And because there are 10 ordinates, so there are 9 equal number of segments. So I got 9. So 0 to 9. The aftermost is the 0, and the forwardmost becomes 9. Area function is multiplied with the lever function. We get moment function. Each area function is multiplied by its lever, and we get the moment function. So 1 into 9, 39 into 8, 312, 73.5 into 7, 514, like that. And H is the common interval which is attached with all of them. Now the moment function is again multiplied by the same lever. So these levers from here, from this column, same levers are copied here. Okay, from 0h to 9h. So multiply the moment function with the levers again, and we get the second moment of area, which is moment of inertia function. This is the longitudinal moment of inertia function. This is the inertia function. Because h is multiplied twice, so it becomes h square. We add all the moment of inertia functions in this column, and I get the sum of the products. Remember, there is h square also attached. This is summation 3. So what is the area of water plane? 3h by 8 is the Simpson's coefficient for rule 2 into summation 1 and multiply by 2, because we have a half breadth. So to get the full area, we must multiply by 2. So 3 by 8 into 20 is 633 is the area function here, summation 1, and multiply by 2, and I get the whole total water plane area 9495 square meter. What will be the distance of center of rotation from aft end? Because my levers are from aft end, so my center of rotation also will be from aft end. That is first moment of area function divided by the area function into h. Okay, summation 2 divided by summation 1 into h. This is summation 2 is the moment function upon area function into h, and I get 83.725 meters. This is the distance of center of rotation from aft end. You can say LCF. So 83.725 is the. And what about now moment of inertia? Because my levers moments I have taken from aft end, so my axis for moment of inertia is also aft end. So longitudinal moment of inertia IL is about the aft end axis AB, 3h by 8 Simpson's coefficient into summation 3, which is the sum of the products of the moment of inertia function h square, and again we multiply by 2 because I want the moment of inertia of the whole water plane. So 3 by 8 into 20, summation 3 is 13947.3. From here, this is 13947.3, summation 3, h square also. H square, don't forget there is h square here. H square must appear and multiply by 2 to get the moment of inertia of the whole water plane. So we get this 8368380 meter raised to the 4. So this is the longitudinal moment of inertia about aft end, because we took levers from aft end. Now this axis which is at the aft end is parallel to the axis passing through the center of rotation. So in order to get the moment of inertia about center of rotation, axis YY passing through the center of rotation, I apply parallel axis theorem. So moment of inertia about aft end axis AB minus AD square. A is the area of water plane and D is the distance between the two axes. Means distance of the center of rotation from aft end. One axis is at the aft end, the second axis is the centroidal axis, which I found the distance of center of rotation from aft end. So moment of inertia about aft end 8368380 here minus area of the water plane, the full water plane 9495 into distance between the two axes, means distance of the center of rotation from the aft end 83.75 squared, and I get 1712503.94 meters to the 4. This is the moment of inertia, longitudinal moment of inertia about the axis which is passing through center of rotation, because this moment of inertia is to be used for calculating BM. The axis about the axis which is passing through center of rotation upon underwater volume. So 1712503.94 upon 112.195.122. I I get 152.636 meter. This is longitudinal BM. So as you can see, the BM transfer was 26 point something meters and longitudinal BM is 152. So it's much larger. And even the moment of inertia, longitudinal moment of inertia is 17125030, and what was the transverse moment of inertia? It was 3019158. So the transverse moment of inertia is much smaller than the longitudinal moment of inertia. That's why the ships roll easily and to a large angle, because transverse moment of inertia is smaller. But the longitudinal moment of inertia is much bigger, so we don't pitch that much. Only few degrees of pitching takes place. That is the reason. Okay, I hope it is clear now. If you have any comments, you can put the comments. But the main thing here was to know the axis about which moment of inertia is to be calculated. On one occasion, the ordinates are perpendicular to the axis. The working is the y cube function. And on the second occasion, the ordinates are parallel to the axis. And there we take the moments from one end. Okay, thank you very much.